Good morning, this is Jim Hendershot. Again, we're ready to discuss the performance analysis of reluctance synchronous machines, and this is lecture number 26. The reluctance machine concept is very old. It goes back before the 1900s, and as late as 50 years ago, Bonita Electric, an old motor company that's still around in Chicago, they took their little line of small induction motors, and they took the rotors, which were die-cast with aluminum bars, as we studied in the induction lectures, and they machined sections out of the OD, machined the bars and the steel poles away, so that this gave, instead of having a smooth OD rotor, that put saliency into the rotor. So they turned this AC induction machine into a reluctance synchronous machine with grid start capabilities. By removing these rotor sections, the parts that had the OD right up close to the air gap of the stator, that had higher reluctance there, and those sections had die-cast bars in them so that it would line start. So the 4-pole version with the die-cast cages with salience that got in the rotor would line start, and then close to synchronous speed of 1800 RPM for the 4-pole machines, the salient poles would pull the rotor into synchronism with a stator magnetic field speed and eliminate any slip. These motors weren't very efficient, but they did make a nice synchronous motor out of an induction motor, very simply constructed. There's modern versions of these being used to replace single-phase AC appliance motors. The efficiency of a simple, low-cost single-phase induction motor can be improved a lot by allowing it to pull into synchronism. Some of them now even use internal magnets like an IPM inside the cage, which pulls them into sync and improves efficiency. So they're becoming quite popular. We're discussing here the ones that are inverter controlled, however. So here we have the simple equivalent circuit of the RSM. It has basically all magnetizing. The magnetizing current and the torque producing current are the same current. We don't have two components here like in induction motors. Here's the vector equations that for the D and Q axis from the synchronous reference frame, the DQ phasor diagram, the Q axis and the D axis, and vectors of the phase current. Here's a steady state vector diagram including the losses. It's a very complicated diagram. The torque calculation for an RSM is discussed here. The most important parameters for any machine, of course, is the output power as a function of current, and then the input power as a versus output power, or the efficiency. These are the two most important parameters. So this is the equation of the to calculate the torque for an RSM, and it's related, of course, to the number of poles. And the current, and it's very dependent upon the inductance ratio, as we keep saying, and here it shows that. Here's the formula for the efficiency. If you substitute the losses in there, there's a resultant RSM efficiency formula to calculate. Now, the inductance ratio is highly dependent upon the air gap, as you might expect, because it is a reluctance machine. There's no extra magnetic circuit in the rotor, and the rotor becomes part of the stator magnetic circuit, and any machine like that has a very critical dependence on the air gap. It must be kept as small as possible. A good way to start, as we've said before, is to use the air gaps in an induction motor of the same size, certainly no larger. That's where you want to begin your designs. And here's a plot of some data that's been calculated over the years. with the inductance as a function of inductance ratio as a function of the air gap length. See how it drops off considerably for identical size motor. And as we've said before, there is a loss of torque output due to the retention ribs, the little webs. Webs might be a better term. The webs used to hold the flux carriers together for rotor stability. And the loss of flux that leaks through those passages reduces the inductance, and then of course the inductance ratio is reduced, and that reduces the torque density. Here's a formula to calculate that, to see what the rib has, how the rib thickness affects the quadrature inductance and the salience ratio. The best way to understand what's going on here is, of course, to do a finite element analysis, and here is an example of the d-axis flux field plot and the quadrature axis plot. The material, the rotor material, is non-isotropic, so the flux distribution is controlled by the material condition of saturation. And as it saturates, or as the flux density increases and the permeability decreases, that changes this inductance ratio considerably. So the only way to really analyze that, our inductance calculations are using analytics, of course, only gives us the near open circuit inductance with only enough trickle current to make the calculation the same as what you would have if you made a measurement. So to analyze the inductance ratio at different flux densities, you have to use finite element. And here's look, we're studying the pictures here for a moment. Notice that here's the direct axis excitation, and so all the flux generated by the stator coils passes very nicely through the rotor flux carriers, with some shorting or leakage taking place where these little webs are. And here, if you move the current vector 90 degrees such that now the flux generated by the windings is trying to get through all these air gaps in the quadrature axis, so it's very difficult. Flux it isn't happy with that path. So it tries to follow paths of least resistance, which is in the air gap and around those little webs, so that's where it saturates. The losses, let's discuss the losses in the reluctance synchronous machine a little bit. They're based upon the same behavior as far as the stator is concerned. The stator losses are based on the same behavior as found in this, because you're using the same stator as an induction machine, then the behavior is similar. The induction machine requires bipolar excitation, as does permanent magnet machines, but the RMS does not require bipolar excitation because there's no magnets in the rotor, and the rotor salient poles are attracted by the stator flux. No matter what the polarity is, it doesn't really care. It's just like attracting a magnet to a piece of steel. The north pole is attracted just as strongly as it is a south pole. Therefore, the stator core experiences the same losses as if we're an induction machine. The reluctance synchronous rotor contains no windings, so there's no ohmic losses. There's no losses due to excitation current. But since the rotor is rotating synchronously with the stator field, one would expect very little or near zero iron losses in normally laminated stators. However, that would be the laminated rotors, not stators. But the rotors that are laminated from punchings that come out of the stator hole, that sort of lamination has no eddy current losses. But if they're laminated axially with the blades going down the axis of the shaft, now there are eddy current paths in each one of those flux carriers, because because they go from one end of the rotor to the other, so there are eddy currents generated in those. Due to the stator and rotor slotting, the flux must jump across slot gaps, so there will be some eddy currents resulting in those due to the slotting, but that should be a minimal amount and not cause much rotor heating or heating at all. Here's an example of a lot of work that was done, and it's described in this book here, this ISBN book, and this was a axial laminated machine that was a two-pole device. So here these were slabs of soft steel, and these slabs here were in fact aluminum in this example, and the inductance ratio in this machine was of the order of 13. It's very high. And this example here achieved an inductance ratio of 10, but it had a very small air gap between the rotor and the stator. This is a phasor diagram of a pole and the inductance ratio for this is about 13 as well. As you can see, the D-axis inductance is 2, and the quadrature axis is 0.15. This should be an L here, not an I. And here's some work that was done to plot the. This was done on, reported in the same book on page 402, and what is shown here is the inductance ratio and the percent of torque production versus the inductance ratio for different ratios, and the 5, the curve for the 5 and the curve for the 10 are actual machines, but the inductance ratio of 50 was introduced for academic interest, just to show what the trend is. Two samples wasn't enough, so this shows how important the torque production is as a function of the inductance ratio. Here's the same comparison of power factor and output power as a function of current angle, and at 3 different inductance ratios reported in the same. This is data that can be used for reference for your design. Here's the formula for the output power from the load angle equation, and it's clear here that the higher the direct axis inductance, the higher the output power and the torque at any angle. But the limiting factor for the output power is certainly the stator leakage inductance. It's very difficult to calculate these two inductances. They can be performed in several ways, including field theory, FEA analysis, and a few circuit approaches. There's a magnetic circuit method explained here by Lippo, Liu, and Antabli in their 1994 paper number 35 from Wempeck at the University of Wisconsin. This method assumes no iron losses, slotting, and skewing, plus a uniform air gap. And we refer to you to that document if you're interested. For my purposes, I find that using FEA analysis for the inductance predictions for various rotor design is my favorite method. So that concludes this lecture.